Pleasure to be back. Pleasure to speak. I'm going to be talking about
a little bit larger than.
Yeah, I'll increase the font. Yes. So this is joint work with Arkadev, Yogesh, Jaikumar, Swagato. We put this out maybe just less than a year ago. It's all my colleagues are in wonderful places all around India, and this is joint. This is work that most of it was done when I was at CWI here, and some of it maybe after I went to Liverpool. So I'm clearly the odd one out. I'm the closest one here, I guess. I'm presenting this. Feel free to interrupt me at any point. Happy to take questions. Interactive is what. So throughout this talk, we're going to be working with Boolean functions, which are objects that take n bits of input and spit out a single output bit. And we're going to be working with DTs, which is, I'm going to repeatedly use that as abbreviation for decision trees. So this model of computation of decision trees, I'm just going to describe how it works via a figure. I think this is the easiest way. So this is an example decision tree. You have internal, it's a binary tree with internal nodes labeled by variables. For example, you can have x1 and edges are values in 0 or 1. And then you have leaves with values again in 0 or 1. Right. So this decision tree that I've drawn here naturally computes a Boolean function on 4 input bits in the following way. On input x1, x2, x3, x4, it first checks whether the value of x1 is 0 or 1. If it's 0, go down the left subtree. If it's 1, go down the right subtree and follow in this similar fashion until you hit a leaf, at which point you output the value at the leaf. Okay. So decision tree is a very natural model of computation for Boolean functions. So I'm going to say that this tree computes f if p of x is notation I'm going to use for the value of the leaf reached on the computation path corresponding to input x. So the tree computes a Boolean function if it agrees with f at all inputs. All right. Good. Why do people care about decision trees? It's of course a very natural, easy to describe model of computation. One key reason why it's so important and why researchers look at it a lot is because this captures this whole model of query complexity. So decision tree can be thought of as a classical query algorithm. I should apologize in advance. There's not going to be much quantum. So if you want to step out already. But the quantum analogs of the statements that I'm going to present as our main results are still open. So this spoiler for the open question part. Good. Yeah, so decision trees capture query algorithms, and in the query complexity setting, you have a known Boolean function f, you have an unknown input x, and you wish to evaluate f of x. And of course, without any knowledge of x, this is impossible. The way you have access to the input is via queries. So you can query, for example, the query algorithm corresponding to this tree would first query the first variable of x, depending on whether it's 0 or 1, go down the left subtree or right subtree until you hit a leaf. Yeah. And output the value at the leaf reached. And the most widely studied cost measure of query algorithms is the maximum number of queries made on an input, which is nothing but the depth of the corresponding decision tree. Right? And one reason why the query model is so interesting and so widely looked at is it's one of the few clean models of computations in which we can prove unconditional lower bounds. Right? So one, I guess, meta or hope is that we translate lower bound techniques here eventually to stronger models of computation where we really care about lower bounds. And then you can also talk about analogs of P, NP, and so on in the query world. And we know several statements that people would be jealous if we knew such statements in the Turing machine world. So we can make statements like P is not equal to NP in this world, P is equal to PPP, P is equal to PQP. So these are all statements that are true in the query. Anyway, it's a bit of an aside. So the query world is a bit simplistic because you don't count for the operations that you do in between the queries. So these are treated as free. This is the main abstraction from the Turing machine world. Now you may ask, what happens if we equip query algorithms or if we equip decision trees with some more power? And that's precisely what we're going to do. Rather than querying single variables, what we're going to do is we're going to allow decision trees to query some fixed functions of variables. Okay. So in particular, what I'm going to allow is, okay, so first I'm going to define D of f. So the deterministic query complexity of f or the decision tree complexity of f is just the minimum depth of a decision tree that computes it. Now, what happens if we allow query algorithms not just to query single variables, but also query, let's say, conjunctions of arbitrary subsets? So I'm just going to say allowed query. At cost 1, instead of just a variable, you're allowed to query such a function. Yeah. Now, if you had to use a regular decision tree to compute an AND on all of the variables, you require depth n. This is fairly easy to show via an adversarial argument. So let's allow that for free. And now I can talk about the smallest depth again of a decision tree that computes f in this model. So I'm going to call that D and of f, which I'm not going to define, but it's exactly this with the tree allowed to have conjunction queries. And define D or of f, the parity of f. So here you allow for queries to arbitrary parities of subsets of the variables. And another measure that we can talk about, like, so the depth of a decision tree is like the time complexity analog of time in the Turing machine world. So we can also talk about the space complexity of query algorithms, which like space, the number of nodes in a decision tree is a natural proxy for space, I want to say. So the number of nodes in a decision tree is up to a factor of 2 equal to the number of leaves. And we don't care about this factor of 2 for this talk. So the log of the deterministic decision tree size of f is going to be, yeah, okay. So the decision tree size of f is going to be the minimum number of nodes in a decision tree that computes f. And if you think about it, the decision tree size would be exponentially large. So somehow log of this quantity makes more sense. So if the log of this quantity is polylog n, say, then you would want to say that your function is efficiently computable by small space query algorithm. Okay, good. Another thing we could allow is both ands and ors. Now you might think this is all very artificial. I'm not going to motivate parity decision trees. These have connections to communication complexity, for example. It's been studied in several contexts. You just Google parity decision trees, you'll get tons of this. This I'm motivated by saying it's the space analog of query algorithms. as opposed to depth being the time complexity. This here has a very practically relevant motivation if you allow ORs of arbitrary subsets to be queried. So this is the same setting as in the combinatorial group testing setting, in case you've seen this. So combinatorial group testing is a model that was developed during the Second World War. And specifically, the US was wanted to test soldiers who had enlisted for the war, whether they wanted to identify sets of soldiers who had syphilis, because syphilis was a big problem at that time. And testing a single soldier's blood sample for syphilis is a bit expensive. So what a researcher came up with is this idea of testing sets of samples altogether. And the test returns a positive outcome if at least one of these samples was a positive case for syphilis. Okay? So in other words, all you're doing is you're testing an OR of a subset of samples, and you get a positive answer if at least one of them was had syphilis material, right? So of course, since COVID became a thing, this has become a very widely studied model of computation. If you haven't heard of combinatorial group testing, it's also called pooled testing. Okay. Need to go back and look it up.
I have a question on like you said that the log at the size is like the space.
Mhm.
But couldn't the space of your algorithm be much smaller if you don't like consider a tree, but like rather like build an engine program or come back together?
Yeah, that's true. That's why this is a bit of a more artificial, I guess, motivation. That's true. A true query algorithm, I would consider the size to be the minimum size of a branching program that computes it rather than a decision tree. But well, at least, I mean, both of these individually makes some sense. And now I'm going to connect the two, and so hopefully it makes more sense to look at size of decision tree. Yes.
Are you querying the no variables?
Good point. Very good question. Are you allowed to query negations? So I'll restrict that over here. You cannot query negations. And if you think about it a little bit, if you allow for negations in these models, it becomes essentially the same model as this one. So this is a folklore proposition, so I don't quite know who to attribute it to. Okay. And I'm going to abuse notation throughout this talk, and whenever I put a tilde above a big O or big omega or a theta, so tildes are always going to hide polylog factors in the input size. So this is truly an abuse of notation. Okay, so this is another motivation somehow for studying log of size of decision trees, because it's essentially equivalent to and or query complexity. Okay? And it's fairly simple ideas. So let's sketch this maybe. So if I want to show this direction, recall that the cost measure in this case is the depth, minimum depth of an and or decision. So if I want to do this direction, what you're going to do is you're going to start with a depth S, say, decision tree for and or decision tree for F. And let's suppose your first query is and in this decision tree. Now I want to convert it to a variable query decision tree here. All I'm going to do is simply expand out this and. So let's suppose the decision tree you started with had this structure. The first query was an and on output 0. goes down to another tree T0. On output 1, it goes down to a tree T1. This I'm going to map to maybe let me say, let's assume this. So I'm going to replace this whole AND query by the most natural expansion into a variable query decision tree.
Sorry, what is T0 and T1?
Sorry. So I'm saying, suppose you started with a tree in the AND OR model that computes F, and suppose that tree had the structure that this is the first query made. If the output was 0, then go into a tree T0, which I'm not defining now, without loss.
Yeah.
So if you started with a depth S tree here, then with a little bit of just staring, you can observe that the size of this tree that you end up with here is going to be like n to the s cells. So if I take a log here, so you're saying if you start with a depth S tree, you end up with a log S times log n size decision tree, and we don't care about log. The other proof I want to do here itself. Yeah.
Is there a function where it's just not useful to do any of these ANDs or ORs?
That is possible, yeah. So for you could have functions for which the regular decision tree complexity is the same as the AND or decision tree complexity. For example, the parity function is going to
Do you then still have like this exponential blow up if you look at the size?
Well, yeah, I don't see the problem. Like you would start with a tree that's already not cheap. So if you start with a depth n tree, you're going to end up with a size 2 to the n tree.
Yes. Okay.
We're taking logs of the size, I guess that's important. So for this side, what we're going to do is you start with a small size decision tree for F that queries only variables. Let's say this is size S. Now, what you can show with the induction, I think, is that there exists a node in this tree such that the subtree rooted at that node has a constant fraction of the size of the number of nodes. So in the sense, the number of nodes in this subtree is between S over 3 and 2S over 3. Now, suppose you have this property. How do you construct an efficient AND OR decision tree? With two queries, if you think about it a little, you can test whether your input reaches this node or not with an AND query and with an OR query. So let's suppose this path was x1 equals 1, x2 equals 0, x3 equals 1. And then this node was this node here. Yeah. So all I can do is I can test x1 and x3 and just x2. That's not very good. X4 equals 0, let's say. And this node was here. So I can test x1 and x3, x2 or x4, and then the answers of these are going to tell me whether my input actually reaches this node or not. Yeah.
But you're not allowed not queries here, right?
So I'm not querying not queries. I'm using ORs for all the 0 edges and
So-
ANDs for all the 1 edges. So with one AND query and one OR query, you determine whether you're here. If you are in this subtree, then you've cut down on a fraction of at least 1/3 of the original size. If you're not, then you're in this subtree, which also has at most 2/3 of the original size. So you've cut down on 1/3 of the original size. So with cost 2, you've dropped S by a factor of 1/3. Repeat this log S times. And then and this all works out. So if you start with the size S tree, you end up with a depth log S tree. I'm going to call this balancing. Good. Now, next, what I want to do is I want to talk about randomized decision trees. The view of randomized decision trees I'm going to take is a randomized decision tree is a distribution over deterministic decision tree. So T mu is a randomized decision tree. I'll talk about its cost measures and so on. But first, I'm going to say a randomized decision tree computes a Boolean function f if you sample a tree from the support of this and run it on X, then with high probability you have the right answer. So mu is a distribution on deterministic decision trees. So essentially, I'm saying a randomized decision tree is a distribution over deterministic decision trees. And the correctness requirement is that for all inputs, you must have, if you sample a deterministic tree from the support, run it on X, you're correct with high probability. And the cost of T mu is going to be equal to the maximum cost of a tree in the support. Now the cost here could be any of these measures that I spoke about. The depth complexity, the decision tree, or D, the query complexity, the AND complexity, OR complexity, parity complexity, size complexity. Yeah. This is the most natural, and this is, I guess, the most natural way of defining a randomized cost measure. And
Sorry, the mu is that you're taking T over a mu distribution over T's?
yes. Yes. So mu is a deterministic degrees.
Sorry, I missed it, Nikhil. This last max is taken over the support of mu. Is that what you mean?
Yeah, so for all T in the support of mu, I'm abusing a lot of notations.
Wouldn't
That have not-
wouldn't it be more fair to say that the cost is the average? Not the-
Well, that's true, but perhaps, but this is how things are defined, right? I mean, BPP, you're not going to go and say we should study average case complexity instead of worst case complexity.
So why would you do this randomized decision tree? Can you like get shorter trees?
Yes,
Because
you can.
Okay, but why wouldn't the following, what is wrong about this? Isn't there a decision tree in your T mu possible sets that exactly computes F to get this probability to be 2/3?
That's possible. So this shows that the randomized complexity is at most the deterministic complexity,
Yes.
but
Okay.
you can get savings.
Okay, so it could be that it doesn't compute it, or
Yeah, so it could be the case that all trees in your support don't compute it exactly. They could be off by a few points, say. But they could all be off by different points. So that's why.
Why don't you put the mu on the left there? Cost mu? Is it like more like a cost mu? Cost T? Because I don't know if you optimize over mu afterwards. So.
Well, I'm thinking of T mu as one single randomized decision tree, I guess. So the distribution mu,
Yeah, but,
really there's no need for this T here, but
yeah.
but what is the max over them?
so the max is over all trees in the support of mu. So all trees that have mu value non-zero.
What if we're
you do max or average, then it more or less the same, because you could always do some sort of Markov inequality to say, okay, I'm not much larger than the, like, at most 3 times the average with.
That's a good point.
2/3, and then just. you
So-
take a little failure probability extra.
That's a good point. We can do one direction that way. The other direction doesn't quite work out.
Oh.
So you can say this
Yeah.
max complexity is at most the average complexity.
Yeah, but
The other way,
but I think, no, the max is complexity and most the average complexity is clear, I'm doing
Yes.
eventually the other direction.
Uh, that argument shows the max complexity is like at most the average complexity.
It'd be one really big tree. that
Oh, sorry,
has
no,
tiny, tiny
yes.
probability, right? That-
Oh, yes, you're right. Oh, sorry, yes, that is what I said. You're right. Okay, now I understand what you're saying. Yeah, okay, so yeah. I agree now.
So you could study the expected complexity, but then a more natural thing to do would be to require that your tree tree computes F always. This is more like the ZPP setting, I guess. And you could do this. And even here there are separations known. So this is the way randomized cost measures are defined. Like in all the most natural way. I don't know how to motivate it better than that. But are there more questions?
Does this 2/3 matter? I mean, you have like easy amplification.
Yes. So you can, since we're not caring about constants and polylog you can assume that's any constant larger than 2/3 with a constant depth below. So there is easy amplification of such trees. Just repeat the tree a few times, take the majority output, some simple Chernoff bounds.
Can you repeat the last thing you said about computing it always?
So if you want to talk about average depth, I guess, then somehow the natural correctness requirement is to require that with probability 1, T of x is equal to f of x.
Why natural?
Then the cost would be the minimum among the t, because all of the t's compute. No, am I confused with that?
Well, all of the trees could compute f. Well, would compute f, yes, but different trees would have different lengths for each x. No, but different trees would have different orders of varying variables for each x. So a lot of trees could find out. So I don't have examples because all the examples doing separations are all complicated, unfortunately.
But these are like based on the minimum there.
Yes.
So these costs, like if you set this probability to be 1.
But you can imagine that the reason for a deterministic decision tree having large depth for f could be caused by a single hard input, let's say. But this hard input somehow in this distribution of trees could be caught in low depth by various different trees in the support.
No, I understand, but that's what it is. You have this probability to third, right? If you put that to 1, then you lose the.
Yeah, but if I put this to yes, if I put that to 1, I will lose that, but then I would replace the max by expected number of queries. Anyway, I think we digress. This worst case complexity somehow turns out to be the most a natural measure of randomized complexity rather than average case complexity. Good. So I get to state theorems now. Already have enough background. Okay, so before this, I want to state a theorem of Nisan from 91. It was first published in the late 80s. It first came out in the public domain in the late 80s. It was published in 91. Like a true complexity theorist, once you have randomized analogs of deterministic models, you would ask, does randomness provide an advantage? Yeah, I mean, I'm sure all of you would think the same if random was replaced by quantum. And Nisan showed that in the setting of decision trees computing Boolean functions, this is not true. So randomness does not provide a super polynomial advantage. And now you could ask the same question: what happens if you equip trees with these additional query, I don't know, additional power to query different functions? And these are our main results. Maybe I'll write it in now.
You're online, that's harder to read, your main results. White. Maybe white is.
Fine, I'll
Yeah.
So if you view Nisan's result as a de-randomization in the query model of time complexity, then you can view our first theorem as a de-randomization of space complexity in the query model. By this proposition here, this means and or queries do not give super polynomial power. Now this is hiding polylog factors, whereas Nisan's result didn't. At the end of the talk, I will address these polylog factors. Right, theorem 2. This is again for all F. So we show that even if you don't restrict to and or queries, if you just restrict to or queries, say, and the same statement holds true with a slightly better poly factor there. Again, I'll address the log factors later. And as you can imagine, the same proof technique that we use for this also shows the same result if you replace ors by ands over here. So this basically says that randomness doesn't provide an advantage in this regular query model, doesn't provide a super polynomial advantage, I mean, in this model, this model, this model, this model. And in this model, it's very easy to see that randomness can give the maximal possible separation. If you consider the OR function that outputs 1 if and only if at least one of the n bits is 1, any deterministic algorithm that has access even to parity queries, you can show by an adversarial argument that it requires n queries.
So you mentioned like the space de-randomization or something, but isn't there some result that like deterministic space and randomized space are related by like 1.5 power or something? How
Maybe
do you know how this relates to that? Like
this is all in the query model. I don't. Are you talking about like Turing machine model results?
Yeah, I guess.
Like RL continuing out for 1.5.
Right. Yeah, yeah, I guess this would be.
Yeah, I haven't looked at that. I guess I'll take a look. It's a nice question.
So is that Nisan bound, that cube there, is it actually sharp, or could you maybe replace it by 2, but you just don't know?
Good question. Yes. So it's not known to be sharp. And the best bound we could hope for there is a 2. So there exists a function for which there's a quadratic separation.
Okay.
Ali, do any of these polynomial bounds hold if you have a partial function?
Okay, another good question. If you allow for arbitrary partial functions, then there are maximal gaps everywhere.
Yeah. Okay.
So
Yeah,
this,
yeah.
it's I guess, total functions somehow admit this magical structure, combinatorial structure, somehow it's exploitable maybe. So if you look at this approximate majority function, which is, let's say 0, if the number of ones in your input is less than n over 3, and 1 if the number of ones is larger than 2n over 3, and it's undefined on all other inputs. Then whatever query model you consider out of these, deterministic algorithms are going to take a lot of cost to compute this function. But randomized algorithms, all you need to do is sample a few ones and estimate whether the number of ones was actually larger than 2n over 3 or less than n over 3. So constant. All right. Okay, so I want to spend a little bit of time on proof techniques. So first, what I want to do is tell you how Nisan proved his result there. So Nisan introduced this combinatorial measure called block sensitivity of F that I'll be defining soon. And he showed that defining BS of F. So he showed at a very high level, showed an upper bound on the query complexity of a Boolean function by the cube of its block sensitivity. And then he showed a lower bound. This is an omega here. Let's ignore constants. So this plus is, combine these two results and you get df is at most order RF cube. And what is block sensitivity of F? I just want to define it quickly. So you have a Boolean function F. Let's suppose you fix an input X in 0, 1 to the n. So a subset of variables B is sensitive. Okay, maybe. Okay, I'll flip this up after this. So a subset of variables is sensitive for an input. If you look at that input, flip the variables in that subset, zeros to ones and ones to zeros, and the function value changes. So in that case, you call that subset of variables to be sensitive for that, so for F at X. So now the argument that Nisan uses to show this, let's not get into it, but this one is just to say if you have a function with block sensitivity K, then.
So what is block sensitivity? Is that?
Sorry, I didn't define it. So you look at an input X and look at the maximum number of disjoint blocks that you can find that are all sensitive. And this maximum is the block sensitivity of F at X and the block sensitivity of F, which is the max over all X of this. We'll look at an example in a second. Yes.
Is B is a number from 0 to n? Is this an index?
No, it's a subset of n, subset of variables,
Okay, good.
indices.
But it's a subset of the which one? The basic is flip of X?
Yes.
Ah,
Yes. Yeah, so this notation, I mean, take X and flip all of the bits in B.
Yeah.
Good. So let's look at an example of the OR function. And let's look at the all zero input. So if I look at this variable here, this is sensitive because F, the OR function on this input is 0. But if I flip this variable, the function value changes to 1. So this bit is sensitive. So is this bit. So is this bit. So all of the individual bits are sensitive for OR. These are all disjoint. And the block sensitivity is at most n because you can have at most n disjoint blocks. So the way Nisan's argument for this proceeds is to essentially say that if your block sensitivity is k, then somehow you embed an OR on k variables. So F is at least as hard as an OR on k variables. Then from first principles, using Yau's min-max theorem, you can show that the randomized query complexity of OR on k variables is omega k. This is a very high level idea. I'm lying a little bit, but so what we want to do is try to adapt this proof. So the first thing that we tried and immediately failed, as you will see why. So suppose the most natural attempt is going to be, let's try to, so I'm trying to prove theorem 1 now, which is the D size result. So I just want to replace all the D's in Nisan's argument by log D size and all the R's by log R size. Naive attempt number 1. So this statement here can be seen to be true. This is because if you have a tree of size S, since we're working with binary trees, its depth is at least log S. If you have S nodes in a tree, its depth has to be at least log S, log base 2. I should have mentioned that. So that inequality, if you think about the directions, it already implies this. This, unfortunately, is not true, even if you replace randomized by decision tree, a deterministic size. Okay? And an example of witnessing this is nothing but the OR function. Its block sensitivity, like I showed you here, is n. But even a naive deterministic decision tree computing F, which is like this, replace the T0s by 0 and T1 by 1. So this is computing the AND function, but you get the idea. It has size n or n plus 1. So if you take logs, you get a log n over here and you get an n over there, which is not good. So this block sensitivity somehow is not the right measure. So what we end up doing is we define a counting analog of block sensitivity somehow. So the idea of Nisan's, but one way to interpret this argument of block sensitivity is order R of F is to say that consider a randomized decision tree. Let's assume it's deterministic for now, for simplicity. Look at the path that this all zero input takes, right? And let's suppose that has small depth. Since it has small depth, it has to have missed some blocks on the way on that path. So that means it doesn't know whether the input was actually this or whether it was any of the inputs with those blocks flipped. So that path must have large depth. This is the idea that you want to keep in mind. And this only applies to depth, as you can see, since we're tracking the path that the all zero input took. And here's our fix for that. We want to look at all inputs combined somehow. And this notion block number, which I'm going to denote by hashtag BS. So we're going to relax this requirement of sensitive blocks being disjoint, and all we're going to look for is minimal sensitive block. So let's look at an example, perhaps. It makes it easier. So if you look at the majority function on n bits, so this is the function that outputs 1 if at least half of the input bits are 1 and 0 otherwise. And let's look at the all zero input. Yeah. Now the majority function is not very hard to show that decision tree is computing it have large size. Any decision tree computing it must have exponential size. So if I look at this input, the block sensitivity is always at most n, because the number of disjoint blocks is at most n. But the number of minimal sensitive blocks is all sets of variables of size n over 2 plus 1. And these are all minimal. Right? And there are exponentially many such blocks, in roughly n to 0. Right? So just the point of this example was to show that this somehow captures more than just block sensitivity. And indeed, the decision tree size of majority is large, so perhaps this is the right measure. And so we do show that this is the right measure. So first, I should say that after we define this, we realize that this has already been defined in previous work. The earliest reference we could find of it was a paper of Kulkarni and Tal from 2016. Similar measures have been considered in the past. Kulkarni and Tal used it for a somewhat related topic of analyzing different combinatorial measures of Boolean functions, but not quite the same. Okay, so maybe in interest of time, I want to tell you the two key statements that go into proving our theorem 1. This is all for all n from n bits to 1. So this is our key lemma 1. That's somehow an analog of Nisan's first step. ds is at most block sensitivity cube. Log d size is almost at most log square randomized size. Okay, there's this extra part which was not there in Nisan's book, but the second step is exactly the analog that you would imagine to that. Which is this a block number is indeed a lower bound on, sorry, I didn't, but we'll define it here, but we'll probably guess. So the second inequality here, the second lemma is indeed an analog of BS is order RF. It's just block number is order log R size F. I wanted to prove that, but maybe let's skip that in the interest of time.
Sorry, so you try to prove this 24, I would not be 30.
Yes. So this is theorem 1 with the 4th power. Yeah. That's one thing I should point out. Thanks. So if you combine these, you just plug in hashtag BS square is at most log square R size. So you get a 4th power separation between the sizes. You're right, we get weaker bounds than Nissan's in this setting. Yeah, we don't have an improvement here, but somehow in the second theorem, we have a 3rd power separation, but that uses some more stuff that I haven't defined here. So just like block number was the key measure over here, it turns out that the key measure in the second theorem is something called zero fractional hitting set complexity, which already is a mouthful and is tough to define. So few words maybe, theorem 1, I'm going to erase a little bit. I should have mentioned this when I stated the theorems itself. So theorem 1 answers an open question. That was actually posed by some of us here. Yeah, 22. So this is Aryan, Cornelissen, and Subha. So we had posed essentially the same question here in a different language. And somehow that's where this project all started that I'm talking about. I was presenting this work at TIFR, and then some people got interested, and then we all joined forces and came up with that. So here this paper was fitting to QSoft. It was a paper on quantum query algorithms, and somehow we asked that question in a different way. So theorem 1 answers an open question that we posed there, and theorem 2 answers an open question of Knopp, Lovett, McGuire, and Yuan, who actually asked exactly this with the ANDs. For AND decision trees, does randomness provide a super polynomial advantage? And a few words on the log factors. If you're one of those picky people who say that log n's in a bound doesn't truly mean this polynomial, super polynomial separation isn't true. So we can get rid of log factors here in this inequality here at the cost of log to the 3 R size. So the statement we can make is log D size of F is order log to the 7 R size of F. If you want to get rid of log factors here, at least one log factor is necessary, in the sense there exists an F for which this quantity is omega log n and this quantity is order 1. So you need to have at least one log factor, and that same case that I just said also holds true here. So we need at least one log factor. So this somewhat satisfying justification of log factors.
What function is that?
Okay, good. So you can think of the threshold function on like 2. So this function is just if your input has 2 or more ones, output 1, otherwise output 0. And if you think about it, if you like OR query algorithm, you can show that deterministic query algorithms require omega log n cost by an adversarial algorithm. And for randomized algorithms, you just test the OR of a subset, test the OR of the complement of the subset. With high probability, if there are 2 1s, then you've got one in each. We can talk about it offline because we're running out. But the threshold 2 function witnesses. That's the log factors. One question, okay, one more statement I should make is that we can actually recover Nisan's result up to polylog n factors. So we can recover just this statement here, plugging in, playing around with this statement a bit, we can conclude this statement as well. So in some sense, our proof is a generalization of that of Nisan. So we get a cubic separation, but with polylog n factors. There's another question of what are the best possible separations, like class asked. You can show that any separation in the query world, regular query world, depth complexity, carries over to separations here. So what I mean is that if you have a function f for which df is omega rf to the alpha, then you would also have another function f prime for which this quantity here is omega log to the alpha r size, and the same thing for here. And currently the best known separation is quadratic over here. And the best upper bounds we have here are 4th power and 3rd power. And of course, one of the most natural questions I think to ask is what happens with quantum. So follow up, okay, I wouldn't call it a follow up, but there was this paper due to Beals, Burman, Cleve, Mosca, and de Wolf that showed the polynomial method implies that such a statement also holds for quantum query complexity on this side. So df is order qf to the 6 for all total functions. So p is equal to bqp in the deterministic decision tree complexity setting. Decision tree complexity setting, the depth complexity. You can ask what happens if you equip query algorithms with ands or ors. I don't know what to think of size as, because quantum query algorithms are not naturally represented as decision trees with circuits. So yeah, that's still the question. And I think let's stop. Thanks.